Hi, I'm Stephen Eshiba, and I'm here to tell you a little bit about how to calculate the thermalization times. And the idea behind the thermalization time is I have a molecule in this room, gas molecule. How long does it take for it to become thermalized? That is to say, acquire approximately the same kinetic energy that all the other molecules in the room do. So the first notion here is we need to know how dense are the molecules in this room. That's the molecular number density. And a way you can get to that is to say, well, it's the mole density, moles per cubic meter, times how many molecules in a mole, okay, which is Avogadro's number. And the N over V part we can get from the ideal gas law that says N over V is just P over RT. And if you run through those numbers, you find that, roughly speaking, at room temperature and pressure, there's about 2 times 10 to the 25th molecules in every cubic meter. Okay, so obviously that's important because the denser the gas, the more frequent collisions there are. So let's go to this Z collision frequency. The idea here is I've got a molecule, gas in this room. How many collisions per second does it experience with other molecules in the room? And your text derives this formula. It says that the collision frequency is this quantity Z, sigma, which is what's called the collision cross-section, times how fast molecules are moving relative to each other, that's C bar rel, times this quantity that we just got, which is the number density of gases in the room. So it's a hope that this is a little bit intuitive. It says that, well, the faster the molecules are moving, that's going to increase the collision frequency. This sigma here, the collision cross-section, goes something like this. I've got a molecule, let's say nitrogen, and I'm thinking that it's going to hit another molecule, and of course the likelihood that it hits that other molecule depends on how big it is. And the way that gets put together is that we imagine this disk here. It has an area, and as long as a molecule is going to even graze another molecule, then there could be a collision. And as it turns out, typical numbers are on the order of 1 nanometer squared for cross-section. Now your text gives more precise numbers for any given molecule, but that's a good order of magnitude. Now, if we want to be in an SI system, I would have to convert nanometers squared into meters squared, 10 to the 9th nanometers in a meter, so that gives rise to that 10 to the minus 18 meters squared. So that's our collision cross-section, 10 to the minus 18 meters squared. Okay, and then, well, fine, we've got that number, that number, that number. Well, C bar rel, we've already figured that, it's on the order of 500 meters per second. This factor of square root of 2 takes into the fact that there's relative speeds that are important. And so we take all these numbers, put them together, and you get something like a Z of on the order of 10 to the 10th, and it's SI, so it's per second. What does that mean? That means a molecule in this room will experience 10 to the 10th collisions every second. Now, it's going to be kind of convenient to think in nanoseconds, so I'm going to multiply this by 10 to the minus 9, so that would be about 10 collisions for every nanosecond. Okay, so that's a good number to know. Your molecule in this room, you experience 10 collisions every nanosecond. Okay, so it's also kind of convenient to think of the inverse of the collision frequency, which is the time between collisions. And thinking still in nanoseconds, that would be 1 over 10, so that would be 0.1 collisions in between, 0.1 nanoseconds in between collisions, okay? So in other words, every 10th of a nanosecond, I get hit again. 10th of a nanosecond, I get hit again. So now the final thing about the thermalization time is you imagine that a molecule's got to get hit, say, 10 times before it's really thermalized and has sort of an average kinetic energy. So this is just a kind of a rule of thumb, where I'll say the thermalization time is something like 10 times the collision time. So 10 times 0.1 is about 1 nanosecond. Okay, so there's our result. The thermalization time for a nitrogen molecule in the room is takes about a nanosecond to become thermalized. Okay.